All right, so let's get started with this topic 0 test on dimensional analysis. So we're just going to go through each question, starting with the dimensional analysis questions. Those are going to be 3 points each, one for the work, one for the right answer, one for the sig figs. I'm going to be pointing out some sig fig things throughout, but let's just get started. So convert 3.05 times 10 to the third meters to miles. So we're going to use a couple different conversion factors shown above. Oh, and we've already ruined everything. Let me just go back up. Here we go. So with this, we're going to start with our given 3.05 times 10 to the third meters, lowercase m. I'll do this a couple different ways. For this first one, I'm just going to go, I know I need to convert meters to kilometers, and I know I need to convert kilometers to miles. And then I'm going to drop my units like it's hot, so meters on the bottom, kilometers on the bottom. For these conversions, the one bit from kilometers to meters is also right here. So I'm just going to plug that in. The numbers for each 1 kilometer is 10 to the third meters. Then for kilometers to miles, 1 mile is 1.61 kilometers. We have 1 mile is 1.61 kilometers. Now, theoretically, this one should be one significant figure. The reason for that is, well, these are equal conversions. They're what's known as an exact conversion, therefore significant figures don't count. This is not an exact conversion. What this test should say is 1.00 miles is equal to 1.61 kilometers, and then each of them have 3 sig figs. But I was going to take 3 sig figs or 1 sig fig, regardless of what you put. I was not going to accept 2 or 4. So with that said, let's get going. When we do this, we find that our meters cancels with our meters, kilometers with kilometers, and the 10 to the third actually will even cancel with the 10 to the third up here. So it's just 3.05 divided by 1.61, and that brings us to an answer of 1.89 miles. All right, moving on. 9.5 times 10 to the 7th milliseconds. 9.5 times 10 to the 7th, that's 2 sig figs. Milliseconds, 2 minutes. So I'm going to convert milliseconds into seconds. Then I'm going to convert seconds into minutes. That should say min, not hour. And then I'm going to drop my units like it's hot, millisecond and second. And there are my conversions. So I'm going to go ahead and look for the second to millisecond. Oh, there it is. 1 millisecond is 10 to the negative third seconds. And then I find that 60 seconds is 1 minute. That is also an exact conversion. So both of these are what's known as exact conversions. I'm just going to talk about it a little bit. Exact conversions are things that can't be measured, or sorry, that there is no measuring tool that changes the accuracy. The definition of 1 minute is 60 seconds. It's not like a year is 365 days, because that's not true. A year is 365.24 days. And even that is not 100% accurate, and that's what we kind of make it. 1 minute is 60 seconds. That is what the definition of a minute is. Just like milli, the prefix means that 1,000 milliseconds is 1 second, or 10 times 10 to the negative 3 seconds is 1 millisecond. Because those aren't measured amounts, they are exact. On the other side of this, a non-exact conversion, something that we do use sig figs for, is 1 mile is 1.61 kilometers. That is, we measured out a mile and we measured out a kilometer and we saw how they compared. So we could theoretically be more exact depending on how good our measuring device is. So that does mean we use significant figures. Anyways, to continue with this, when we do the math, we get that 10 to the negative third changes this to a 4, 7 minus 3, and then it's 9.5, or 95,000 is divided by 60, gets us an answer of 1.6 times 10 to the third minutes, or 1600 minutes. Both are correct, but two significant figures. All right, moving on. Number 3. Now with this one, the first thing I did is I actually just bounced the decimal point back so I could start with significant figures, and I got 5.43. And now these zeros are after a decimal point, so they're significant. 5.43000 times 10 to the negative fifth kilograms. And I'm going to convert that to grams. So I have kilograms to grams, and I will drop my kilograms like it's hot. And then I'll use my conversion. 1 kilogram is 1,000 grams. When I write this out, I find that I get 5.43 times 10 to the negative second grams. And now that would be incorrect actually, because look at me not carrying over my sig figs. We need our 1, 2, 3 zeros. This should be 6 sig figs, or 0.054300 grams. Both these are accurate and significant. All right, convert 1,040 inches per second to kilometers per hour. We need one more thing here. We need to convert our miles to our feet. It was a conversion that I gave on the test, but just in case you don't have it, 1 mile is equal to 5,280 feet. That would also be exact because the definition of a mile is 5,280 feet. So we'll start with 1040 inches per second. So I have a couple conversions here. First, I need to convert my inches to kilometers. So I'm going to do inches to feet. I'm going to do feet to mile. I'm going to do mile to kilometer. And so I'll drop my units. Inches will go down. Feet will go down. Mile will go down. So I'll carry these over. I know that 12 inches is 1 foot. 5,280 feet is 1 mile. 1 mile, 1.00 miles is 1.61. That again being the only non-exact conversion. Lastly, I need to convert my seconds to hours. Now, this one's a little different. We have seconds on the bottom here. And if seconds is on the bottom, to cancel out the seconds, we need to move the unit to the top. So when I convert seconds, I will put seconds on top, hour on bottom, which is good because we know that we want kilometers per hour, which already has the hour on the bottom. And we know it's 3,600 seconds per 1 hour. Again, that's an exact conversion. We'll cross out our units. Inches cancels inches, feet with feet, mile with mile, seconds with seconds. You'll notice we end with kilometers on top, hours on the bottom, exactly where we want to be. We plug this whole thing into our calculator and we get an answer of 95.1 kilometers per hour. Now, I know this is 3 significant figures because here I have 3 on both, and then our starting amount 1040 is 3 significant figures. If that 4 had a if that 0 had a decimal, then it would be 4, but it doesn't, so it isn't. Now, number 5. 49.3 grams of carbon dioxide, 2 grams of water. Now, here's the thing. This uses real conversions, but we don't actually need to know those conversions or where they come from at this point. We just need to know how to plug in our conversion factors. So I'm going to start with 49.3 grams CO2. I want to go to grams of water. So you might ask, well, how do I go there? Well, I'm going to look at my conversions. I see that grams of CO2 can only go to moles of CO2. So I'm going to go mole on top, CO2. Looking at my conversion, I've used this bottom one. And then I see that mole of CO2 can convert to mole of water. So I'm going to put mole H2O. That's 2 of the 3 conversions. I see the last one says mole of H2O and grams of H2O, and that's what I want. I want grams of H2O. So I can just figure out from the conversion factors how to get there. This is true dimensional analysis. You may not know the conversions, but understanding the way that the conversion factors interact with each other in this area to get what you want, that's the key. I will drop my units, gram CO2 on the bottom, mole CO2 on the bottom, mole H2O, and I will fill in the values that we need. 1 mole is 44.01. We have 2 mole, 4 mole, and 1 mole is 18.02. All right, so when I do this conversion, Something fun of note is that this is actually a weird example where this top number, the mole values, all the mole values are exact numbers. We don't worry about them for sig figs. But the gram values are not exact values. They have significance, both of them having 4 significant figures. Regardless, we're going to use our 3 from here. So when we go through this and we do our conversions, we find that we have 10.6 grams, 10.6 grams H2O. Alrighty, that is that. Moving on to this next one. Number 6, I took out of the test because I made a mistake. I gave you the wrong conversion. The conversion I need to give you was 1 mole H2O is equal to 6.02 times 10 to the 23rd molecules H2O. And what I could have actually even given you was just 1 mole is 6.02 times 10 to the 23rd. The reason this would have worked is because you can convert 1 mole H2O. We do our conversion. We go to molecules, mole, and 1 mole, 6.02 times 10 to the 23rd. And when we do this, we actually can cancel out the mole, not mole H2O, mole. And then we end up with molecules of H2O as the remaining units. So I screwed that one up, so I just removed it from the test. The answer would have been something like 1.11 times 10 to the 24th molecules H2O. So if you want to go back and try that one, now that you have this conversion here, give it a shot. All right. Convert 19 grams per milliliter to kilograms per gallon. 19 grams per milliliter. I'm going to first start my grams to kilograms. Kilograms on top, I will drop grams on the bottom. And I know that from a previous problem, it's 1,000 grams is 1 kilogram. Now I have milliliters on the bottom, and I'm going to move those milliliters up to the top to liters. It is 1 milliliter, it's 10 to the minus third. And I see liters on the bottom, going to put that on the top, go to gallons. And I see 3.785 is 1.00 gallons. I'm adding those 0.00s. This one, again, I would have accepted 1 sig fig or 2. And you get 72 kilograms per gallon. Just to be clear, I'm going to cross out my units. Milliliters with milliliters, liters with liters. All right. Moving on to the last one. There's a couple ways to do this, and I left some space just so I could explain both of them. And it kind of depends how you want to work through it. I'm going to start off with, what I think might not be the simplest, but is definitely one that might help you understand why these conversions work. 9.4 times 10 to the 7th milliliters. And we're going to convert that to meters cubed. So the first thing I'm going to do is I notice that I can convert milliliters, so our volume liters, into centimeters cubed also being a volume, but using the unit of length, centimeter cubed, milliliter. And it's a 1-to-1 ratio, very nice. Metric system works great. Now here's the thing. In my conversion, I'm only given centimeter to meter, but I need centimeter cubed. Centimeter cubed means centimeter times centimeter times centimeter. And so what I can do is I can do meter, centimeter, and 1 to 10 to the minus 2. I can do that again. Meter, centimeter, meter, centimeter. 10 to the minus 2, 1, 1, 10 to the minus 2. And each centimeter will take out one of the previous centimeters until all 3 centimeters are canceled. And what we end with, milliliter cancel with milliliter, we end with 9.4 times 10 to the first meter times meter times meter, or 94 meters cubed. And that's a long way of doing it. There is a much simpler way, which is where we go 9.4 times 10 to the 7th milliliters. We'll do that first conversion exactly the same, 1 centimeter cubed, 1 milliliter. But the second one, we will just do 10 to the minus second meter, 1 centimeter, and we'll cube the whole bracket. This cube will not only apply to the units, but it will also apply to our values. Now, 1 cubed is still 1, so that doesn't change. But what this ends up being is 1 centimeter cubed over 1 milliliter times 10 to the minus 6 meters cubed over 1 centimeter cubed. And then we can get our nice little cancellations, and we still get 94 meters cubed per, sorry, just 94 meters cubed. Either way, both good ways to do it. I prefer the bottom one. All right, experimental design and separation techniques. We can go through these pretty quickly. I'll use a highlighter. Two solids are mixed. Which of the following best describes the situation? Solids are generally heterogeneous mixtures. We can usually separate them, and we usually separate them by physical means. That's kind of the definition. Which of the following does not describe a homogeneous mixture? So basically, we're describing a heterogeneous mixture. A homogeneous mixture does not have visible boundaries. It is one uniform thing. It's quite literally B. That's one of the fun things about this one. We don't need to look at these because A and B contradict each other. Only one of them can be right. And so what you're going to find as we progress through the IB curriculum is IB tests allow you to eliminate things purely by test taking techniques. And I'm going to beat on this point so much. And that is, if you have two contradictory answers, the other two don't matter. Only one of them can be correct if it's like which is true or which is false. If they are so opposite, only one of those can be the answer. And so it's that. Yeah, we can have homogeneous mixtures that are liquids, and homogeneous mixtures can be separated by distillation. Distillation, which is not chemical, it is physical. A mixture of two liquids results in the precipitation of a solid that forms on the bottom of the container, which would best describe the process to separate the solid precipitate. When you have solid from a liquid, just think you're going to filter. So using filtration. So B, using evaporation, that would help. However, it comes with this caveat that we're going to also leave the precipitate and a crystal of a previously dissolved compound. So we don't want that. We don't want the previously dissolved compound. We just want the solid. Distillation is for liquid-liquid. It would also leave some dissolved solid possibly. And then recrystallization is not for necessarily separating, but it's technically purification as well. So anyways, filtration is solid from liquid. Which of the following is false regarding distillation? When the solution is vaporizing one of the chemicals within a solution, it will hold a constant temperature. That's how it works. That is quite literally the process of distillation. Distillation can be used to separate two or more solutions if they're liquid homogeneously. Yes, that is described further up. Distillation works on the principle of liquids having varying boiling points. This and this one corroborate each other, actually. They literally make each other make sense. So if one of those was wrong, both of them would be wrong. And then lastly, distillation cannot separate two solutions if one has a higher boiling point than water. Well, of course it can. It just means the water is going to boil, and then the other solution is going to boil. So yeah, that one is false. And that's what the question's asking. Which one is false? All right, last. Looking at the image of chromatography experiment below, answer the question regarding it. Assuming the solvent, the liquid, is water, which of the colors, A or B, has a greater interaction? How do you know this? Very simple answer, A, because it moves higher up. Because it moves more or higher up the paper. A good way to sometimes think about like chromatography is if you have a flowing stream of water moving in one direction. Something that interacts really well with the water, like maybe a little toy boat. is going to move with the current of the water. Something that maybe doesn't interact with water, like maybe a rock, will just kind of sink down and maybe it'll move a little bit as it gets pushed along. But because the water really can't carry it, it can't interact with it in a way, it will not move. And that's kind of how these things work in chromatography. As water moves up the paper, the ink that matches the water's polarity specifically and is also maybe smaller or lighter will move further than the ones that don't. So with that, that is the whole test. Hopefully you got everything right. And if you didn't, you can see how or where to fix your mistakes. Have a good one. Bye.